Okay, so let's play a bit with these ideas. Maybe first an example, maybe of very simple applications. So let's say I want to compute on a domain that I'm going to describe the function x2 plus y2 dx dy, and my domain is half of the unit circle on the right of the y-axis. What do I mean by this? This thing. Okay, that's assuming that we're a well-drawn unit circle. Okay, so okay, and I want you to compute that. So it shouts for polar coordinates. Why? Because this is a domain that I can very easily describe using polar coordinates, and furthermore, even the function is going to be very easily described with polar coordinates. So let's do our substitution. You remember three things. First, we should know how we want to write the bounds. So in that case, it's going to be rho. Well, obviously it's going to be between 0 and 1 because that's the inside of the unit circle. And I want theta to go from negative pi over 2 to plus pi over 2. Okay, so if I write the rho first, that's going to be 0, 1 minus pi over 2 plus pi over 2. Then I've got my function to change. Second thing to change, that's exactly rho square. Don't hesitate to pause and go on the exercise by yourself. Okay, and then I have to change, third thing, I have to change my dx dy into d rho d theta, and you know that that should be rho times d rho d theta. Okay, because that's what we found earlier, that the dx dy should be equivalent to. Okay, and then you just perform your integration. That's going to be negative pi over 2 plus pi over 2. So I've got rho cube. So that's going to be 1 over 4 plus 1 over 4 of rho to the 4 between 0 and 1, and d rho, well, d theta. So that's going to be 1 over 4 times integral between negative pi over 2 and plus pi over 2 of the one function d theta. So that's just the size of that interval, that's pi. So the result is pi over 4. Okay, that's a very simple and very direct application. Okay, let's do something else. Now let's imagine I'm giving you the problem in a fairly different way. Let's say that I'm asking you to compute this integral. Okay, double integral on the domain of a function, let's call that f tilde of rho and theta, d rho d theta. But that's unlucky, but your domain is a rectangle. So that means a rectangle. It means that a nice rectangle that you can express very easily in Cartesian coordinates. So that would be x between two values, let's say a and b, and y between two other values, let's say c and d. Okay. All right, so that's unlucky, but in Cartesian coordinates, that's a very easy description, but in polar coordinates, it's going to be awfully hard to describe. Okay, so you have to do the contrary. You have to go from polar to Cartesian coordinates. So let's assume that, well, we know how to write the function. So, well, let's see what we have. First, we change the bounds of the integral. So this time it's going to be very clear. I'm going to have AB for dx and CD for dy. Okay, then let's assume you know how to write your function. So that's your function in terms of polar coordinates, and you know that it's equal to some function of the Cartesian coordinates, right? So this, well, usually we do the contrary, but let's say it comes very nicely. And so you change your function. And third thing, well, you change the d rho d theta. Okay, what did we have earlier? We had that dx dy, that's what we used, was equal to rho d theta. Okay, thing is that now we've got the contrary. Okay, no problem, we're going to use that. That just says that d rho d theta is equal to 1 over rho dx dy. But the thing is that in my integral that if I write it like this, 1 over rho dx dy, is that a correct writing? No, obviously not, because, well, rho shouldn't appear in my new integral because I'm doing this substitution. So I just have to re-express whatever depends on rho and theta as a function of x and y. So that should be 1 over square root of x2 plus y2 dx dy. Okay, so instead of rho here, I should really have 1 over square root of x2 plus y2 that's appearing in my integral. Okay, and well, you see that's kind of very direct. Well, it's also something that you could have derived without, well, without using explicitly this formula, just by thinking that when you write your substitution, you will usually write dx dy is equal to absolute value determinant of the Jacobian of phi du dv, if these are your new variables. That's the basic formula, where phi is the function such that phi of uv is equal to xy. Okay, but the thing is that if you have it given, if you want the other way around, what does it mean? It means the other way around means that u and v are given by phi minus 1 of xy. Okay, and so you know that, and furthermore, you know that the Jacobian of phi is equal to well, if you invert the Jacobian of phi, that's going to be equal to the Jacobian of phi minus 1, and that also stands for the determinant. Okay, the determinant of the Jacobian of phi minus 1 is going to be 1 over the determinant of j of phi. Okay, so that's why here above here we really found 1 over the determinant of our Jacobian matrix. That's absolutely normal, but the thing is that I have to express this using my new variables. Okay, let's do one more example, keeping that in mind. A very simple substitution. Why? Because that's the linear substitution. What do I want? Let's say I've got my variables x, y, and I want to substitute two new variables. Let's call them capital X, capital Y, where capital X is defined as ax plus by, and capital Y is equal to cx plus dy. Okay, and you can even add, if you like, plus alpha plus beta. It just means that it's a real change of basis in the Cartesian plane. So it's really something very easy. Okay, so let's consider alpha and beta equal to 0, but you could really try it with the different values, so not 0. Okay, so how should we work that? xy, you can that's a linear substitution, so you can, well, you can remark that you can write this as a b c d matrix times the vector xy. Okay, and what you get that this is going to be a valid substitution if you can go from old variables small xy's to new variables big xy's and back again. What does ensure you that you will be able to get back again if, let's call this matrix A, so that's going to be a valid substitution if A is invertible. Okay, so that's pretty clear. When you have something linear, you don't even have to go to any Hart's theorem. It just comes directly, anyway, the Jacobian of this transformation would be also the matrix A, and you need it to be invertible. Okay, but then what do you get when you've got some double integral d of f of xy dx dy, and for some unknown reason I want you to write it as an integral with respect to the new variables capital X, capital Y. Okay, so let's assume you would find easily a way to write your new bounds. You find also a way to write your function. Question is what comes here. Okay, so that you get an equality between the two integrals. What comes? Do we have anything that comes in front of the d big X, d big Y? Take a few seconds to think about that. Did you find that? So the answer is that you get 1 over the determinant of A, absolute value of the determinant of A. Okay, so pay attention to this kind of things. The formula I've given you is when you've got phi of uv is equal to your old variables, and then you get that dx dy are equal to determinant of Jacobian of phi times du dv. Okay, that's the formula you have to remember and also know how to use. Okay, in our case, what plays the role of the uv? Well, I've called them big X, big Y. So what you get from this, and even you can see it as well, if I'm if I write it line by line, okay, if I just do as you would proceed before you had the formula, what would you get? You would write that you've got ax plus by. You would write capital Y is equal to cx plus dy. You apply differentiation, okay, on both sides. Okay, I don't know if that's the kind of notations you use to write, so let's write it this way. So that what would that give you? Line by line, you would get dx is equal to a is just a constant, dx plus b dy for the first one, and dy is equal to c dx plus, well, too bad I've got 2 times the letter d, but d is my constant d, and here d is the differentiation. Okay, and so if you can find, if you solve this system, you can find dx in function of with respect to dx dy, and similarly find dy in function of dx dy, and then write what your product dx dy would be equal to. Okay, but what would you do actually in the end? You would just invert the matrix ABCD. That would just involve inverting matrix ABCD. Okay, so you could also find it this way, right? So, but be careful when you've got this kind of thing. How is your substitution given? Okay, do you have like these new variables with respect to old variables, in which case you really have to take the inverse of the Jacobian, or do you have old variables with respect to the new one, in which case you just have to compute the determinant of the Jacobian directly. Okay.